Welcome to Essential Problems with Crip. This will refer to photoelectron spectroscopy and how to read uh, these scans and determine what element they are based upon the tools of electron configuration. These type of problems really presuppose that you have a good grasp of writing electron configurations. So you should definitely, at this point, be comfortable with using the periodic table and knowing the order of how subshells relate to each other, right? And that's why the periodic table is really helpful here, right? Going in order 1s, 2s, 2p, 3s, 3p, 4s, 3d, etc. Okay, so what is photoelectron spectroscopy? It's a technique that's used to analyze a substance and really the subshells to look at where the electrons are located in the subshells of that substance. And it does this by using a high energy source of light, typically X-ray light, high energy X-ray light. And as this light comes to the sample, here we have a nice little equation here, which is when that light hits the sample, then it will excite electrons, and electrons from different sublevels will actually be emitted, right? Because this is high enough energy to ionize the sample. And those electrons will be emitted and then go to a detector, okay? And we don't need to focus on how this detector works. It just will hit this detector with a certain kinetic energy. So this little equation here is in reference to the kinetic energy of our electron, right? And so this H nu, right, is in reference to the incident energy of the photon of light, right? Because H nu is equal to the energy of that photon. So the kinetic energy of the electron is equal to the energy of the incident photon that's coming in, right, minus the binding energy of your subshell. So the way this works is that all this light is coming in the same, right, the same energy, but if you have a less, like a less attracted electron, so it's on the outside, let's say it's on a higher sublevel, right? Well, that's going to have a lower binding energy, and so that electron, when it's emitted, it will have more kinetic energy. It'll be moving faster, and so it hit that detector with a high speed. Versus an electron that's really attracted to the nucleus will require a much higher binding energy, right? And so that means that electron will be moving slower, much slower when it hits the detector. And that's kind of what we're doing here. It's just kind of mapping out the electrons according to how quickly they're traveling. Of course, we can interpret that data and then create a graph. And so we get a graph like shown below. This is actually taken from an AP exam question. And so you notice here's the graph, right, in binding energy. So we're already kind of doing the calculation necessary to solve for binding energy. Of course, you could just rearrange this equation to solve for binding energy. And then we're kind of mapping out the electrons, their relative number of electrons that are hitting this detector according to their binding energy. So here we have twice as many electrons here that have this level of binding energy versus over here half as many compared to this have much less binding energy. And so it's important to note that these graphs are usually from very high and to low binding energy. It's a little bit different from typical graph. You have to keep that in mind. So let's look at some graphs and see if we can identify some of these elements. So here, actually, I have in order on the periodic table the elements. So without question, this is hydrogen, this is helium, lithium, etc. Okay, but more importantly, you need to develop a technique to be able to identify any element just by looking at the scan itself. And the best way to begin this process is always to identify 1s. 1s will always be the lowest energy the lowest energy level. So that means it will require the greatest amount of energy to be emitted, to be ionized. So because it's in that lowest energy state. Remember, that's the lowest potential energy state. So if you're looking at these graphs, right, it's very easy to determine which is 1s because you really are looking for the first peak coming in from this axis, right, from the highest amount, right? So as we're going, that's 1s. As we're going along, that's the first peak. That's 1s. That's the first peak. 1s, 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 1s. Always the first peak is 1s, and that will always be associated with that the highest amount of binding energy for that element. So what's interesting here is comparing binding energies between elements. Notice here, this is less than this is less than this is less, this is less than this is less than this is less than this is less than this. It's constantly increasing in binding energy from going from one element to the next. And there's a simple reason for that. There are more protons. Each element is distinguished by the other based upon their number of protons. And if you increase the number of protons, your attraction increases. And so you can kind of, if we were to line these up, and I'll provide a PDF on Google Classroom for you to see this, you'll see that they're all being shifted to higher energy required in order to be emitted, in order to be released. So with that in mind, once you identify 1s, and if you know your electron configurations, then you just follow along. Now, the thing to keep in mind here is sometimes graphs will give you number of electrons. However, sometimes graphs might just say relative number and actually not give you a easy way to determine the number. But in this sense, you can always kind of figure it out if you have a frame of reference to compare. So for instance, like this element x, here we know that this must be 1s. Well, if this is 1s, right, and I actually have another peak, that must be 2s. And considering the fact that an s sublevel can only hold at maximum 2 electrons, well, if I actually have a 2s sublevel, I must have filled this before I entered the 2s sublevel. So this must be 1s2, this must be 2s1. And so if this is in its ground state, right, if I'm identifying the element according to its electron configuration, this must be lithium. 3 electrons, it must be lithium. 1s2, 2s1. Conversely, notice how this one's a bit more shifted, right? For element Y, this first peak must be 1s. This second peak must be 2s. Notice they are of the same height, and so they're the same relative height. This must be 1s2. This must be 2s2. And if we look on the periodic table, it's beryllium. So if we return to here, now notice this is actually a little bit easier if you're just given the number of electrons. It's right there. Must be 1s because it's the first peak, and 1s1. So of course that's hydrogen. Here we have 1s, right, and 2 electrons. So 1s2, helium. 1s2, 2s1, lithium. 1s2, 2s2, beryllium. 1s2, 2s2, and now notice we have our next little peak here, right? And looking at the periodic table, we're going into the next sublevel. Notice the relative size again. This must be boron. Again, notice the relative size here. So 2 electrons, 2 electrons, 2 electrons. Again, going in order. 1s2, 2s2, 2p2. This must be carbon, right? And here we've got 2p3, nitrogen, 2p4, oxygen, 2p5, fluorine. So again, I'll just, for sake of argument, continue with it. So, here we have 2 electrons, 2 electrons, 6 electrons. So this must end in 2p6. That's neon. Here we have, again, now 2p6. We're starting a new sublevel, right? That's going to end in 3s1. This is sodium. Here, again, the peak is getting larger. 3s2 we're ending in, so magnesium. Notice we then begin another, right? So you can see the relative sizes are completely consistent with your electron configurations, right? So this will end in 3p1. This is aluminum. 3p2, silicon. 3p3, phosphorus, right? 3p4, sulfur. 3p5, chlorine. 3p6, argon. And we're not going to really go into that many complicated electron configurations using photoelectron spectroscopy. Honestly, we really won't go much into the D block or the F block. But just for sake of argument, I would like you to see this. Here, of course, we're starting our next sublevel. So this is 4s1 potassium and 4s2 calcium. So I've got one PES scan in which we're going into the D block. And so it's kind of interesting to note this. Again, we're going to talk about this in the future, which is notice here's the 4s2. So this is kind of a little tricky because it's a little different from what you might expect. Notice 3D1 is over here. But it kind of makes sense once you consider the fact that 3D is part of that third energy level. Okay, and we'll discuss shortly when we talk about periodic trends why we're actually filling 4s before 3D, but then why when metals get ionized, they actually lose electrons from 4s first. So that's kind of like an exception to what we're going to be seeing. Again, vast majority of the time, actually in our quiz, we won't work with the D block, and on the AP exam, they don't really refer to the D block either. So really, what you need to just be keeping in mind when you're doing these problems is being able to do all of those configurations that are for the representative elements, being very familiar with them. Till next time, Crit.